Okay, so lecture 15. So today we are going to study system of differential equations and how do we use the apparatus we have so far of eigenvalues, eigenvectors, diagonal matrices in order to solve such a system. So it's going to be a very simple lecture, and maybe in the next lecture we are going to see the applications of this thing. So consider a very simple differential equation in one variable. Now the solution is clearly e to the power of 80. And how do I know that? Well, I just differentiate this guy and I recover back x, this guy back. So this is the solution of the differential equation. Now, one thing to keep in mind is that if I have I'm looking for complex solutions. Let's say I had a complex number and I was looking for. So I note that each of these guys, the real part as well as the imaginary part, satisfy the same equation. I can write it as dz by dt equals to ace of z. So the real part as well as the imaginary part satisfy the same equation. Now this formalism can be taken to seek a differential equation of the form where x is now the column vector x1 t, x2 t, xn t, and A is some matrix, so on and so forth. So in case A is a diagonal matrix, case 1, A is a diagonal matrix. Well, this guy is simple. So for example, I have the column vector by dt is equals to some diagonal matrix with eigenvalues lambda 1, lambda 2. That's my A, and my column vector x over here. So this is just a way of representation of the equations dx1 by dt equals to lambda 1 x1 so on dxn by dt equals to lambda n xn, and I know the solution of these guys. So that is life is simple when I have the diagonal matrices, and I'll get the solution to these equations. But what happens when A is not a diagonal matrix? In general, A can be some A11T, A1N, or anything like any matrix like that, and I have a xt to be x1 t, xn t, so on and so forth. So I'll consider the case. Let's first consider the case when A is an n cross n real or complex matrix and xt is an n dimensional vector. So in other words, what you have is I have this array of differential equations, and I have a11 x1 t plus a12 x2 t, so on and so forth, a1n xn t. A n n x n t, so on and so forth, a n1 x1 t. So this is a system of homogeneous first order linear constant coefficient differential equations. And the idea is to seek the solution of these guys. So I just represent this as dx by dt equals to ax. We already saw when A is a diagonal matrix, this is really easy. But really we want to transform this into some sort of a basis by a choice of basis into some other coordinates where I have this guy, such that this is diagonal and I'll be able to solve the problem. So a change of basis I demand is something like which takes my original matrix to some transform matrix, and my coordinates would be related by these guys. And once I have this, I'll get and I know the solution of these guys since A tilde is a diagonal matrix now. So I have some solutions is, so if this guy is a solution to the above, then I just need to transform this solution is the solution for my original problem, which was this guy. So that is all there is to it. I think if we do some examples, that would be much easier. But essentially, that is the idea. So that's the proposition. If let A be an n cross n matrix and let P be an invertible matrix such that PA P inverse is diagonal. Well, with diagonal entries, the eigenvalues lambda 1, lambda n. So the general solution of the system dx by dt equals to ace of x is nothing but x equals to p inverse this guy, remember, where x tilde I is equals to c of I e to the power of lambda I t. For some arbitrary constants c of I. So that is all there is to it. So for example, I have a, let's say the matrix A is 3, 1, 2, 4, and I can ask what are the going to be the P matrix for such a matrix? Well, it's going to be related to the eigenvectors of this matrix. So that's going to be 1, 1, 2, minus 1. These column vectors are the eigenvectors of the matrix A. And in this basis, A tilde is nothing but the eigenvalues that show up on the diagonal. And well, according to my theorem, what do I have? I have the solutions of the transformed equation uh, in which, in a basis where the A tilde matrix was diagonal, that is given by these guys. So I just take these solutions. So writing these solutions, I'll have x1, x2. The actual solutions are nothing but given by these guys. So I just multiplied by P inverse. That is there to it, which is nothing but C1 plus 2 C2 C1. So in other words, every solution is a linear combination of two basic solutions, x1, x2 is and x1, x2, which are related to the respective eigenvectors and eigenvalues of the original matrix. So that essentially is the idea, and I'll just write down one more proposition, very much in line with what we discussed at the start of the lecture regarding the uh, if you are seeking complex solutions in the real part and the imaginary part both satisfy the same equation, so we can translate it directly even for a system of uh, these differential equations. So let A be a real matrix and let T be a complex valued solution to the differential equation, this guy. Well, the idea is that the real and imaginary parts of xt solve the same equation, just like we saw for the scalar case. Same equation. Okay, so maybe in the next lecture we can do some examples of this sort of a how do we use such a formalism. Thank you.